Hello, everybody. Recording is in progress today, Thursday, March 24th, 2022, and we are approaching the end of the term. Next week would be, maybe Wednesday would be the last class, and we'll be done with our material. So I'll work towards the handout 11 and 12 today, and next week I just uploaded the class notes that has more examples, and we'll do like a quick review, the final exam format, how it will look like, and also the arrangement for the tutorial for the group assignment and the final exam. So yesterday we stopped on handout 11 at the examples. In handout 11 here, everybody can see my screen. Yes, no? Thank you, Colin and Andrea. So we talk about the concept of reduction. And if you remember, we said this one, it's reduce, that mean. And we said that we can inject a polynomial running time algorithm B inside algorithm A, and the input A will be the input to B, and the output will be going output of A, and at that time we said B reduces A, or A can be reduced by B. So the same concept when we talk about logical expression and using the Coq-Levin theorem, and we said the satisfiability of A1 or A2 or A3 and A1 or A5 and etc. So today we'll have the first reduction example, and we said the 3 SAT. What is a 3 SAT? It's a version of SAT where each clause has 3 variables. What do you mean by a clause? This is a clause. This is a clause. This is a literal, and this is the operation, and, or, and the complement, which is not. So A1 or the complement of A2 or A3, and the complement of A1 or A4 or A5, etc. Click, it's a graph with G and N. Is the problem where a given graph G and a number N, decide if there is N nodes in G that are fully connected to each other from an N click. For example, if you were friends with 2 people on Facebook who were also friends with each other, your social graph would contain a 3 click. Theorem, 3 SAT, reduce to click. What does that mean? How we would prove this? First, you would show that you can convert phi into an associated graph G in a polynomial time. By associated, we mean that phi is satisfiable if and only if G contains a 3 click. More details, see theorem 7.32 in your textbook. Theorem, click is NP complete. This is the theorem, or the assumption. Proof, it is easy to see click is in NP. Evaluating an assignment can be done in a polynomial time in phi. Only problem is in NP, are polynomial time reducible to click, because only problem in NP reduced to 3 SAT by Coq-Levin theorem. And we saw that 3 SAT reduced to click here. Example 2. In the class note, I explain more on this. I would explain the example more. And we'll see the graph, we'll see the node, we'll see the clicks all together. Example 2. Proof SAT is a polynomial time reducible to acceptance problem for Turing machine. For example, SAT is reducible to a Turing machine. Proof. Let B an algorithm for solving SAT and C be an algorithm for deciding a Turing machine. Whether a given TM M accept an input S, we can construct B such that it turns in an instant of SAT into an instance of a Turing machine in a polynomial time. See the next slide, how we'll do that. B accept a string phi corresponding to an instant of 3 SAT, which means 3 clauses of logical or Boolean operation. Phi, it defines a Turing machine M, C below, and passes M and phi to C and return whatever C return. B of phi, the function B of phi, construct a string that contains the couple or the pair M and phi, where M is description of a Turing machine M that runs on phi with the following behavior. M loops through all possible assignment of phi. If a truth assignment tau, here in the slide it's T, in the class note you will find it tau, such that phi of T equal true. M halts and output accept. Otherwise, M tries to the next assignment. Out C, given that C of M and phi, which is this pair, call C to decide if M ever accept phi. Return out C. Proof. Continue. We need to prove 2 things here. The first thing, B decide 3 SAT, and the second thing, B runs in a polynomial time, not including the call to C. M eventually halts and accept if phi satisfiable. If phi is unsatisfiable, M loops forever. By definition, C accept M and phi. If and only if M accept phi, and by simply output what C output, therefore B accept, and if and only if phi is satisfiable, therefore algorithm B decide the 3 SAT problem by Cook-Levin theorem. Clearly, B runs in polynomial time, constructing a string M and phi, takes polynomial time in the size of phi, and outputting C's result take polynomial constant time. And you know, in big O, we said that the constants, the multiplication by constant, we forget and we take, for example, 2n, we'll say it's a big O of n. So ATM is NP hard. And we said that NP hard, that's the most complex problem. All the problems in NP are polynomial time reducible to ATM because all the problem in NP reduced to SAT by Cook-Levin theorem. And as we saw, SAT reduced to ATM. Notice we didn't say ATM is NP complete. For that to be true, we would also have to show ATM was in NP, which means solutions are checkable in polynomial time, except ATM is undecidable. Thus, it is not in NP because it's undecidable. So it will be clearer when we talk about those things in the this class note, summarize handout 10, 11, and 12. So here we'll start talking about those, how the NP and the complement of NP, NP completeness. This is a clearer function of what we have in the handout. Here we will do how we prove the reducible, also by a graph, proof of theorem 2, Cook-Levin theorem, how we will do these things, how we will prove it. This is the tau, and this is the phi, it's satisfiable. So we'll explain this, and this is the click issue. This is how we map the text. He said each node in the clause 1 has to be connected to clause 2 and the clause 3, and the same for clause 2 and the clause 3. We will see those in details on Wednesday. and we'll reach to the end of the course. So now today, let's continue with handout 2, whatever we can. Then in Wednesday, we'll complete the handout to 12. Then we'll go to the class note. At that time, we'll be done with our course material. The complexity class, MP hard and BPP. MP hard class. Recall the MP complete. Complexity class was defined as the set of problems that are in NP, and every problem in NP is polynomial time reducible to problem in this class. The second property is interesting because it captures the idea that the problem in this class are hard to solve, but easy to verify, if you remember last class. The NP complete problem, they are hard to be solved, but once if you bring a solution to me, it's easy to verify that it's a correct solution. Let's get an example to be understandable for you, that if you have a very hard game, very tough game, and there is a stage that you cannot solve, you cannot pass this stage. If one of your friend came, hey, look, this is a solution how to pass this stage and move to the next one. It's easy for you to verify that his way is easy. It's easy to verify that his way is correct. But you try and try, but it wasn't easy for you to pass this stage by yourself. So if somebody came to you with a solution, it's easy for you to verify the solution. However, the solution was very hard to find. Is that clear, guys? Yes, no? Answer in chat, yes, no? Okay. So we said that NP complete are problems that very hard to solve, correct? Yes. But if somebody came to you with a solution, and said, hey, this is the solution for your problem, it's easy for you to verify that his solution is correct or not. Clear now? So MP complete problem, they are hard to be solved. But if somebody bring a solution to me, it's easy for me to verify it. This is what I mean. I hope this is clear now. Okay, so what about the first condition? What if we just want to look at problems that are hard to solve, regardless of whether they are MP or not? It's a hard problem. It's hard to be solved, whatever it's MP, P, whatever. So let's define the NP hard. So let's consider the class of hard problems, regardless of whether they are in NP or not. So a problem is NP hard if all problems in NP are polynomial time reducible to it. Translation of this definition, NP hard is a set of a problem that is hard or harder than any NP problem, which is, we said that NP, they are hard problems to be solved, correct? NP hard is the hardest set of them. I have something difficult, but there is a part is the most difficult. NP hard are the most difficult problems to be solved, whatever they are, NP or not. Let's examine a few consequences of this definition of the NP hard classes. It contains the NP complete classes, which we know since last class that it's hard to be solved. It includes problems that are not in NP. It includes a problem that are in decision problem. It even includes decision problem that are undecidable. So it's the most hard problem to be solved. Okay. So this graph, we have P NP, NP complete, we said that's the hardest, which is part of NP hard, and there is NP hard, which is harder than NP complete. Clear till here? Questions? Okay, Ardia. Okay, we answer this here. Ardia was asking, they are just decidable problem or never mind, or decision problem? No, it's include both. Now, to me, we defined it last time. P, it's deterministic polynomial time problem that's solved in a polynomial time. NP, it's non-deterministic polynomial time problems. What the difference between deterministic and non-deterministic? That deterministic, I have only one path to solve or one route to reach to the end. Whatever, it's accept or reject. The non-deterministic, there are multiple paths, multiple possible paths. Some will decide, some will not. They will run at the same time, but I have to calculate the running time of each single path, and the total would be the complexity of that problem. Clear? Yep. So, one of the most hard problems in our life as engineer is the optimization problems. And if you go to your graduate study, most of the research are going toward optimization in telecommunication and networking, 5G, LTE, wireless communication, whatever. Even in my specialization, the artificial intelligence and machine learning, we try to hyperparameter tune the algorithm parameters to get the best result with the lowest computational complexity using optimization technique, hyperparameter optimization. So the optimization, one of the hardest problem that we work, which is minimize or maximize something. So NP hard contains NP complete decision problem, but it also will known for containing optimization problems. Find the best, cheapest, fastest, smallest solution to particular problem. What do we mean by optimization? I have a problem. I need to find the best solution, the cheapest one, the fastest one, the smallest size in memory, the fastest one in running time, the minimum of complexity. This is the target of optimization problems. Here are just some few real world situation that you encounter hard optimization problem. Scheduling. To schedule task in an operating system, you took operating system thing, right? Course. Or you are taking now. I believe it's first semester, third year, right? Guys, yes, no. Is it first semester, third year, the operating system course? Okay, so you took scheduling a problem. First come, first serve, critical semaphores, all of these topics. So want to find the best scheduling algorithm, especially when you took the cloud computing course next year. So in the cloud, in a data center, when I have an HTTP request or HTTPS request, and I'm in the queue waiting the server to run my request. So scheduling these requests and this user, this algorithm, this task on the CPU or in the data center or in the mainframe or in the server, whatever, those are a headache. So optimizing these problems to find the fastest, the cheapest, the smallest solution, the quickest solution, or a quick solution, rapid solutions, keeping the high availability, those are not easy problem to be solved. Data mining or machine learning, how to get data or information from data. Selection. When you have a decision tree and you need to select. Diagnosis problem. Classification. Is this request attack or not attack? If it's attack, what kind of attack? And you need to run it in real time, because you as a user on the net, when you send your request, you need a quick response. So I have to decide these things in a very quick way. I need to optimize my solution to be very fast and high reliable and robust. So this problem, the optimization problem, is not an easy problem. For example, my specialization is optimizing machine learning, which lie under data mining and classification in AI. I spent the last 7 years just doing research and optimization. Done? No, it will never be done. And mainly we concentrate on complexity, how to find easy solution. It's a hard problem to be solved, but I have to provide a solution that is robust, fast, accurate, high available, quick response. All these properties should be available in my solution. So it's not an easy task. So, example, the traveling salesman problem. Given a list of cities and distance between each city, find the shortest route. A, visit each city once, and B, returns to the starting point. More generally, giving a weighted graph, find a Hamiltonian cycle with the lowest weight. Application, scheduling, route planning, etc. Those problems need an optimization to find the minimum, the shortest, the fastest path to pass by all the city with the lowest weight of this graph. All these cities. So this is the source from David Robert, so you can click on it and read more about this problem. The knapsack problem, another example. Giving the knapsack problem with that can hold up to a certain weight. A list of items, each with a weight and corresponding value. Fill the knapsack with the highest value selection of item without exceeding the knapsack's maximum load. So here we need a resource allocation, financial planning, and cryptography. And those are one of the most hard problems in computation. So optimization versus NP. How do optimization problem relate to NP? Are they related? Here's a natural question. Is a traveling salesman problem in NP complete? Basically, no. TSP. Ask to find the best solution. So it is clearly not a yes-no decision problem. Thus, it's not an NP. Okay, what if we restated it's a decision problem? Here, certificate, claimed solution. Is this the best solution? Is this in NP? For it to be in NP, it must be checkable in a polynomial time. But checking it's the best would mean being able to decide it was less than all other solutions. But some optimization problems go to quadratic, go to exponential, not polynomial. Here we are talking only in polynomial, but some problems, they are not polynomial. They are more than polynomial. But we still use this solution because they're still the fastest and the best. Till now, we might find better solution in the future. So we can convert the basic TSP problem, which is NP hard, but not NP complete, into one that it's NP hard and NP complete as follow. Giving a weighted graph and the weight W. Is there a Hamiltonian cycle below weight W, this point is subtle, which is why you will see people refer to TSP as MP complete problem, even though it is not. Technically, it is not. Also, we have the probabilistic algorithm or probabilistic Turing machines. We call the deterministic Turing machine DTM follow a single computational path, whereas a non-deterministic Turing machine NTM can potentially follow many paths simultaneously at the same time for certain types of problems, such as brute force search. So the non-deterministic Turing machines provide a decisive performance advantage. They can explore exponentially more computational paths per unit time as DTM can do, assuming, of course, P not equal MP. And I told you, I'm one of those who believe P not equal MP. Some believe yes, but mathematically, scientifically, not. And still, it's an open problem. It's a $1 million question. Recall, for a problem to be in NP, any single computational path can be evaluated by a DTM in polynomial time. So, in a sense, could efficiently decide an NP problem if and only it had an efficient way to decide which path to take. This would imply P equal MP, which of course we see it false. We conclude it to be false. Here is an idea. What if we picked a computational path at random? When I have multiple computational paths, I pick one randomly. That is, at each step that non-deterministic Turing machine branches, we let a coin toss decide which path to follow. It is not really non-deterministic because it doesn't branch, but it's not really deterministic either, since it's follow paths by chance. So if I decide not to follow all paths of non-deterministic Turing machine, and I start flipping the coin, which path, this or this, this or this, or this or this. So we are trying to find a solution by chance. However, it's not deterministic yet, because I might use this or this, A or B, path A or path B. So probabilistic Turing machine, PTM, is a Turing machine that has access to a source of random bits. When faced with more than one legal next move, to PTM uses the random bit to pick exactly one path to follow. So they are trying to minimize the number of paths to follow. But do I have, at the end, I will reach to a decision or a decidable Turing machine or path? Might be not. It's by chance. So I'm still depending on chance, probability. So the PTM, it will pick random computational path, leave us on a better of than a DTM, which has a single path. So if there are, for example, 2 to the power n computational path and only m of them accept, for some less than or this symbol means it's a way less than n, then we have small chance the probability will be m over 2 to the power n of picking this path at random. But if we add another ingredient, the ability for the decision to be wrong sometimes, we might this lead us to exponential growing, not polynomial. And at that time, it's not an NP problem or a P problem. The class BPP, bounded error probabilistic polynomial time, is the class of problems solvable by a probabilistic Turing machine in a polynomial time with an error probability of at most 1/3. The choice of third as error bound is mainly by convention. Ultimately, any number less than half, 0.5, would suffice. So you can choose like 1/4, 1/5, whatever you choose. The idea that BPP problem are one in which associated a probabilistic Turing machine A halts in a polynomial time, B is right most of the time. So the path that we pick randomly is right most of the time. Those are the assumption, and it will halt in a polynomial time, which is not the case always. It's by chance. To be more formal, L belongs to BPP if there exists a polynomial Turing machine, a probabilistic Turing machine M, where for all string X, M halt in a polynomial time. If X belongs to L, output accept, which is 2/3 of the cases. If X not belongs to L, output accept which is 1/3 or the third of the cases based on our assumptions here. Does primes or prime number belong to BPP? One of the classic BPP problem is primes. Primes is X where X is a prime number. The first major prime test due to Fermat, you can read about his theorem here. However, a certain class composite number called pseudo primes will always pass the test. P, M, a Turing machine, accept X is a composite pseudo prime equal 1. Fermat test, therefore, isn't in BPP since the error probability exceeds the bound for certain input. An extension due to Miller and Rabin provides, also you can read about this here, an unconditional probabilistic algorithm error is bound across all inputs. So the error is available always. So Miller, Rabin, test 1, side, no false negatives. What do you mean by false negatives? What do you mean by false negatives? It's decided as false. However, the decision was false, which means wrong. However, it is true originally. So small chance of false positive, P output prime input was a composite, and this should be less than 1/4 to the power K for K trials, which is the number of your trials. No chance of false negatives. P output composite input was prime equals 0. So after only 20 trials of MR test claims, the input was prime. There is less than 1 in a trillion chance the input was composite. So these things, primes belong to P. So P output prime input was composite equals 0. What does that mean? The fact that prime was found to be in P underlines the sometimes like staggering difference between complexity theory and complexity practice. Consider an irreal test due to Edelman and Rumley. The ARP test like ask it is deterministic but has the following non-polynomial complexity. So it's not non-polynomial complexity. So 3 consecutive lens, which is the natural logarithm of the number. By definition, it is not polynomial because its exponent is in function n. So those are slower to be run, but they are practical solution and we can achieve based on them the purpose. Does P equal BPP? It is yes or no, guys? What do you think? It's one of another open problems in computer science and software engineering. We don't know the answer. So BP, BPP, NP, NP complete, NP hard. This is the classification, and it's still one of the open problem in theory of computation. Do you want to read for more open problems? You can go to this link and read. Questions? So next Wednesday, we will have like an hour. We'll start at what time normally we start? 10:45, right? Yes, I believe 10:45. Yes, thank you, Tammy. Thank you, Colin. So we will again come over the material again and explain the important things that need to be understandable, and we will reach to the end of the course. So see you next Wednesday, guys, at 10:45. If you have a question, don't hesitate to answer now. You don't have, you are free to leave. Have a good day. Thank you. Thank you. Have a good weekend, Brandon. Zachary, too. Nicholas, do you have a question? Ardia, do you have a question?
Yeah, I just had a question about non-deterministic Turing machines. So the class NP is the class of problems which can be solved in polynomial time by a non-deterministic Turing machine, right?
Yes.
So can we not build a non-deterministic Turing machines and then we'd be able to solve these
There
hard
are
problems?
some problems, they are non-deterministic by nature. So if you remember the DFA and NFA, we found that there are some problems we cannot solve them by DFA, right?
Yeah, yeah.
There are multiple paths, there are multiple possible paths. Not all of them will lead me to an accepted state. However, I have to consider them. So next class with example, it would be clearer for you. But it's a kind of Turing machine that we have to deal with in computation.
Right, but like physically, like in the real world, is it like could we possibly implement non-determinism? Like what
Yeah,
about
we
with
already implemented a non-determinism problem, but they are decidable. The problem is they are undecidable. Here is the problem. I don't mind if I have non-deterministic Turing machine, but it's decidable. You need to read the handout, I think 8, when we talk about recognizable and decidable.
Oh, okay.
So
Okay.
I need the Turing machine, whatever it's deterministic or not deterministic, to accept and halt or reject and halt. This is what I'm looking for. I don't want to go in an infinite loop or no answer. At the same time, I have to differentiate if the Turing machine that it's take long time, I might believe it's in an infinite loop. However, the problem is difficult and it takes more time from the computer to give me an answer.
Okay.
So these are the problems that we are facing in computation. For example, in my PhD, one of the problems kept running for 24 days
24
till I get
days.
the answer. In a server, not in a PC.
How like how were you 100% certain that it would halt at some point?
After I was believe it will take like a week, but I don't believe it will take like 24 days. And the first trial after 16 days, the server go down. Then I have to repeat and wait another 24 days.
Oh my God. So total more than a month.
Yeah. So we have still in the computation problems that require massive amount. Some problem they need years.
So will quantum
are those
computing,
undecidable? No, they are decidable, but the machine require more time to run it.
will quantum computing speed up the computation for a lot of these problems?
Of course. Those problems in 1990s, we cannot solve them because it's beyond the capacity of even At that time, we have the supercomputer. It's
Yeah.
beyond its capacity. Now,
Right.
some server, they have features and capacity and computational power more than supercomputers in 90s.
Yeah.
And you have it as like a workstation at your home.
Right.
And at that time, it was $millions. Now you can get it less than $10,000.
Right.
So, computation science is growing.
Mm-hmm.
However, we still have an open problems.
Still.
We don't find a solution yet.
When like when you're working as like a real software engineer, so like not a computer scientist, like more working on the system.
More practical side.
Yeah, more practical. Like, do people still think about this stuff or talk in these terms? Like, how important is
No,
it?
now, for example, if you are developing a system,
Yeah,
like to Best Buy,
yeah,
so you will tell them that we need a server, that the capacity, we need a database server, we need so now these things are available and cheap. So sometimes you didn't concentrate as a software engineering in a complexity thing. But when you are talking about a data center, you are in Amazon or in Google and you are building your data center, then you have to concentrate on those things to use the minimal resources, which we call it resource allocation.
I see.
So on those, no, we have to be careful. But if you work like an application developer in a bank, or these things are not that much important. However, why we teach you this? To know as a software engineer that there are a problem still unsolvable.
I see.
Yeah.
I see.
So yeah, for example, this course will give you an idea to understand what's going on, the computation thing. However, in practical side or in business side or in professional side, you will use the complexity in certain cases.
Right.
Yeah.
Right. Yeah. Like when we do like interviews and stuff, they ask us to implement algorithms and ask us like, what's the runtime complexity?
Yes.
Yeah.
So this is why we teach you those from the scratch. In order, computer, what is beyond that? What are the problem? How it's developed? Is there a problem are unsolvable yet? Because when you talk to people, normal people, that hey, there's a problem not solved yet by computer. Some people, they think that the computer can solve anything.
Yeah.
No, they have to understand this is still a machine.
Right.
And it ran my instruction as a programmer.
Right. Yeah. No, it's all very interesting stuff. Like I'm very much enjoying this course. I mean, I'm enjoying it so much that it makes me think like, oh, I should get like a master's or PhD because it's cool stuff.
Okay, wish you the best of luck. It's not a bad idea to continue your graduate study also.
Yeah, I will. I'll think about it. Thank you so much for your time.
You are welcome. Have a good weekend.
You do. Bye.